Right, we are recording. People coming in, 40 people. That's pretty good. This is the last class before New Year. So congratulations, you've made it this far. Okay then. Now, so look. What am I going to do now? Let me go into... Okay. I think Skino's it's a bit noisy actually with your mic. Okay, great, thanks. Yes, right. Let me go into screen share. Just as I say that, people coming in. Seem to have quite a lot of people today, actually. Let me just go into screen share and get rid of all that rubbish and have a quick look at last week's stuff. Somebody's still doing that. Don't like that very much. But you can have a quick look to make sure your stuff came through all right. As I say, if there's a problem, didn't come through, let me know. But it seems to be working quite well. It's quite a difficult one last week, and I sort of left quite a few things without giving you, much of help. But just to get you thinking about some of these things, I'll be covering a lot of this stuff again today. Okay, but looks good. People working hard. Oops, people coming in. Right. Can't do anything because people coming in. Okay. And that's that. Good to see people trying this more than once. Why not? Yes, that's that then. So anyway, that's recorded, so you can always check that later. Should be no problem. Okay, let me just get rid of that. And let me see what I'm doing. Here, let's go here. Let's have a quick look at last week's stuff. As I said, it was a little bit difficult last week. There's a few things I didn't really prepare you for very much. Predicate. And again, we'll be going over this again today, right? So, if you did it last week, did your best, then that's great. Predicate. Yes, predicate. Basically, it means like a verb. That's an easy way to think of it. And shared intention, cooperation, collaboration. We'll be going into this a bit later. We're looking at machine language very briefly, I suppose. It's an introduction to computer science, machine language, and computer programming. And thinking about language, machine language compared to human language. What's the difference there? And it seems that we've got these ability to collaborate and cooperate, and we kind of understand each other as that kind of animal, and maybe computers can't do that. Anyway, have a think about that. Spelling. Better able to work together to achieve a goal. Yes. Let's check the date of these. That's right, isn't it? Yeah. Okay, good. At the age of 1, children start to show other people things. This will be quite important. I mean, thinking about machine language, computer language. What are we actually doing with that, right? How are we actually communicating? And compare that with humans, where it seems like when we speak, we're kind of presenting something to people. Start to point to other people things. No, it doesn't work there. Show other people things. Yes, I think it has to be. All right. The study of language in use is called pragmatics. Now we're going to go into that next, right? After we cover formal semantics and machine language a little bit, get you thinking about that a little bit. We'll talk about pragmatics next semester and finish it off. Not sure. Yes. Okay, good. And the main idea of pragmatics is that language use is cooperative. I think it's, we can say that, right? That when we use language, we're cooperating, right? The way we understand language in use is we kind of think, okay, that person is cooperating in some way, giving me something useful, giving me something maybe interesting, right? And that's how we understand it. And then you kind of have to think, well, what about machines? Do machines, work that way? Maybe not. We're trying to cooperate and communicating with each other. We usually don't have to speak directly. Nice job. Yes, because we have to think, oh, that person means something, right? And it's not the direct statement, right? And then Tomasello and Dan think evolution of language is a very slow, long process. That's right. That's kind of the big difference in linguistics. People like Chomsky saying that universal grammar suddenly, boing, one day, one moment, pops into our heads, and our mouths and speech organs are already fully developed for speech. That's what he thinks. And everybody else says that's impossible. It must have been very, very slow and very gradual over millions of years, really. Yeah, I mean, really millions of years. Not thousands of years, millions. And Noam Chomsky thinks that the ability to use language emerged suddenly by random mutation. That's right. Doing a bit of a review here. And then semantics, let's have a look. Semantics has made a big contribution to computer science. Yes, we've covered this a little bit. I'm going to go into this again today. Research science, that doesn't quite make sense. Okay. In the days before computers, people relied on printed tables. That's right, nice job. Well done. To do calculations. I don't think I actually gave you that in class, so that was good. This is a review. Charles Babbage, remember him? I'm going to do a little bit again today. Difference engine, nice job. Well done. By the mid-20th century, we are ready for the first digital computers. Good job. Nice. Okay. Digital usually refers to use of the series of 2 digits 1 and 0. Good. So this is no problem, right? Now that's kind of important. We're going to look at how machine language and computers develop. It's based on the idea, basically you've got two numbers, 1 and 0. You think of that as true and false, or on and off. Yeah. And once you get that, it makes sense what's happening in semantics. Okay, Richard Montague, again reviewing this, said there's no difference between human language and machine language. Just think about that. Right? Think about whether you agree with that. Language in use, it's cooperative. That's what pragmatics tells us. We understand each other. I know you're cooperating with me. You know I'm cooperating with you. Is that the case with machines? Maybe not, eh? In propositional logic, sentences are represented as letters, that's right, such as P and Q. Nice job. Code, not quite, I don't think. In propositional logic, any proposition sentence can be either true or false. Okay, now we're going to review this again today. But just get the idea, right? What's going on here? Many students from this university go to work in IT. Many people become systems engineers. I think most students who become systems engineers come from a humanities background, so they're bunke students very, very often. And many Tsuru students do go into that kind of area. So it's worth thinking about that in relation to language. True or false may be represented by the numbers 1 and 2. 1 and 0, sorry. Not 1 and 2, 1 and 0. Ones and zeros, true and false. This is like modern computing, where calculations are determined on the basis of whether electrical signals are on or off. Yes, that's right. For computers, when electricity is flowing, When the signal is on, this is like the one state or true state. Yes, well done. This is good because I didn't go into this very much, right? So you got the idea here. And I'm going to kind of review this again today. P equals 1 means that P is true. Very good. Careless miss. P equals 0 means that P is false. Good. Not P can be indicated with the symbol this. What's that? Minus. Good. And I didn't actually give you this very much, right? So it's nice that a lot of people got that. It'll set you up for today. This is minus P equals 0 mean not P is false, right? So not P is false. If not P is false, then P is true, right? If P equals John is hungry, then not P means John is not hungry. Very good. Nice. Okay. P, now, maybe I didn't go into that, but it did. Okay, this is good. P like that, right? This means if P, then Q. Very good. Many people got that. If P, then Q. If P is true, then Q is also true. Yes. Good, good, good. Not P, then Q. If not P, then Q. Yes. I didn't actually give you that much this, so you work this out for yourself. That's good. That was my intention. If P, then not Q. If P is true, then Q is not true. Yes. Very good. Somebody coming in. All right. No problem. P equals John is hungry. Q equals John. Somebody coming in again. Okay. Okay, if you just come in, don't worry too much. It's all up online. It's on YouTube. I'll be putting it up later. Okay then. P equals John is hungry. Q equals John works. P then not Q. This means if John is hungry, John does not work. That's right. Good. No problem. Bit of a comprehension question, but you can see this is quite simple, right? It's all really just not true, true, not true, on, off, and use pretty simple calculations. Now, but this is at the root of computer science and semantics. In propositional logic, propositions such as P and Q have no internal structure. Very good. Yes, got the hint. Well done. Ideal structure. Good guess, but no. Illegal structure. Like that. It's good. No. Predicate in logic means like a verb. Very good. Like a Boolean. Nice. Okay, we'll be covering some of that again today. Eats JK in predicate like this might mean that John eats kimchi. Yes, very good. Yeah. I mean, it doesn't have to. Eats for a machine. If it could mean anything, right? You can just say, but you can use eats. It doesn't have to be eats because the machine doesn't know what that means, right? Could be anything, but it probably, right, might mean John eats kimchi. That's probably the most common sense. I mean, if you're doing programming, you want to use words that make sense to you so you don't, so it's easier to remember. People coming in. Okay, and then not punched JB, that that might mean, for example, that John did not punch Bill. Yes, no problem. Be careful with the grammar. Country X, yeah, we're doing this again today a little bit, but everybody got it, no problem. So this is fine. Country X, X equals Japan country. Yes, Japan country X, Japan. Yeah, I can't remember how that works actually. Yeah, country. Did I do that right? Oh, okay. I can't figure that out now. Actually, I better check that. 38. Better make sure that makes sense. Looks a bit funny. Anyway, you all got it right just about. Anyway, gave X, Y, Z. X equals John. Y equals Bill. Then Z equals money. Then John gave Bill money. Yes, that's right. It's good. Propositional logic and predicate logic have been useful in the development of computer programming. Very good. So you get the idea here. And we're going to do a little bit of a review of this again today. Computers are great because they're very fast, but they're also a bit stupid because they only understand ones and zeros. Yes, these are all perfectly okay. Ones and zero. Yeah, I'm not going to accept that. Grammatically, it's a bit funny. Walks Jim In the example above, the predicate has one argument. Very good. Wrote bill book. In the above example, the predicate has two arguments. Yes, yes, yes. Donated gym, $100, City Hospital. In the above example, the predicate is donated, and it has three arguments. That's right. Donated X, Y, Z. X equals Tom. Y equals $10,000. Z equals to the university. The above example could mean that Tom donated $10,000 to the university. Oh, sorry, 10,000 yen. Sorry, to the university, and that's where the yen works in this case. Yes. It's not dollars, is it? No. Okay, that's all right. How many arguments would a predicate such as runs have? Yeah, it's probably going to be one, right? Like I run, you run, he runs. Yeah, it's probably going to be one, not two. Four, no, right? You could have any number for putting information into a computer, of course. But for verbs, I think 3 is probably the maximum. Of course, we have adverbs. How many arguments would a predicate such as eats have? 2, good. Eat something. I eat bananas, that kind of thing. 1 is possibility, right? I'm not going to give that though, because I don't want to encourage that. Because I've eaten, right? I ate already. That's one predicate. That's true. But I think the more natural idea is 2. How many arguments would a predicate such as gives have? 3, nice. I give you a book. It's 3, right? How many arguments would a predicate such as read have? It's going to be 2. Yeah, probably. Yeah, I understand what you mean with 1. I mean, that makes sense because the way we use language sometimes is like we only use 1 argument, but usually if you think of read or the verb read, usually somebody reads and something is being read. How many arguments would a predicate such as is a genius have? 1, good, nice. Yes, you got the idea. So that looks pretty good actually, guys. Better than I expected, to be honest. So I don't think we've got any particular problem there. This is, I better go back in here. What's my number 38? I couldn't figure that out. Let me just have a quick look at 38. This is taking a long time. That's the wrong one. God, stupid. Sorry. 12, 11. That's the one, isn't it? That's it. And, right, let me see. 38. 38, 38, 38. Where is it? Japan, country. Yeah, I think that's all right. No problem with that, is it? I couldn't figure it out because they're on different lines, so it makes sense now. Okay, then. Right, I think that's all right. So we're going to look at this today. Again, it's going to be a little bit of, think about computers and machine language a little bit, really to get you thinking about how we communicate, right? What is human language and how do we use human language? Let's compare it to machine language and see how that works. The magic word today is semiconductor. Semiconductor. There it is. Semiconductor. And you're thinking, what is he doing? If you think about semi, right? Semi, it's like half and half, right? Half. Well, half is going one way, half is going the other. 2 states. Yeah, there's 2 states, on or off. That's what it's about. Okay, then. So anyway, let me just come out for a second, see if we have any. No comments. And I think we're okay. Right then. Good. No problem. Right, let's get started. Don't forget, semiconductor is the magic word. Right. And where is it? I can't find it. Oh, here we are. Right then. So basically, I'm going to be thinking about predicate calculus essentially, and predicate calculus is important in semantics, but it also has connection with computers. Anyway, let's think about computers and what happens with computers, right? So I'm going to kind of look at this a little bit. I'm not going to go much, right? But let's get you to think a little bit about it. Really, the point is to compare, right? For you to have a little think about human language, human communication, and machine language, machine communication. Just have to think about it, have a bit of fun, right? So anyway, the earliest computing device was the abacus. Yeah, you know that's Soroban, right? And this goes back about 4,000 or 5,000 years. So 4,000 or 5,000 years ago, human beings needed to do little calculations. It keeps a record of calculations and kind of remembers for us. So you move these things over, you get to a certain number, and you move things over, and you keep it there. So it's a tool, and it helps us to do calculations. Some things these machines can do better than us, so they can remember things better. They just stay when you move the thing over, and it just stays there. So it's like a memory. It helps us to remember things. And 5,000 years ago, human beings were buying and selling things. They were keeping animals. Societies were becoming more complicated, more complex. And so there was a need for calculations. So it has like a memory. So the memory now is like, they're better than human beings at remembering stuff, right? Certainly you just move it over, it stays there. We don't have to remember it. It makes life a little bit easier. And as I say, this is about 4,000 to 5,000 years old. The abacus. And there were other, over history, there were other machines that were being used going back quite a long time. The astrolabe, for example. Astrolabe, I don't know how to say it. And this was used particularly on ships, where it allows you to discover where you are, your position on the sea, I suppose, usually, right? You're using this machine, and you're using the stars, and you're finding out where you are. And this goes back a long way, right? So people were doing these calculations, particularly as people were traveling on ships to distant places. They needed to know their positions. So the astrolabe, I don't know how to say it. That was one of these early calculating machines. And then you had the slide rule, for example, right? And this was generally used for multiplication and division. It's about 400 years old, so this is relatively recent. Yeah. So the abacus goes back 4,000 or 5,000 years. The astrolabe goes back about 1,000 years, I think, and then the slide rule only about 400 years old. So there you can see that, and some of these are quite complicated. So machines for helping us do calculations. And if you think about history, then machines for measuring time, clocks, in other words, have been quite common. Here's a kind of egg timer using sand flowing through this funny little bottle thing. This would be using the sun to determine the time. And water, the flow of water in some cases, a water clock. So, time, the measurement of time became important in society as it becomes more complex. And I suppose also as we work together in societies, we work together to do things, then management of time becomes more important. So in a sense, it kind of comes back to cooperation. It's like, if you are working in a company, you have to be on time because, everybody's working together. And if you don't know the time, that's a problem. Yeah. So kind of coordination with other people, working with other people, time becomes important. And you can see, like, some of these clocks were very complicated. Look a bit rusty here, isn't it? Becoming more complex in structure. Mechanical devices ticking away, going up 1 second, 1 second, 1 second, up one, up one, up one, things like that. So basically, all these tools, the basic idea is they make us cleverer. They give us extra power, which we wouldn't have otherwise. We're probably not very good at knowing time. Sometimes it's like somehow I know how much time has passed, but sometimes it's a bit difficult. So these things are kind of helping us to live in society. They make us cleverer in a sense. So let's think about computers. The word computer was originally a job title. It's not a machine. I think I covered this last week. So a computer was a person who did the computing. And sometimes they use machines like the abacus, for example. So in other words, if you got 5,000 years ago, the computer would be the person, right? The person using the abacus rather than the abacus. You got Leibnitz step reckoner. That was one of the earliest calculating machines. And then if you look at this, 1694, in a way, not so long ago, right? Only about 300 years ago, just over. Kind of recent. And these were kind of really fairly basic calculations, adding and subtraction. Even those machines are kind of really big, cumbersome things. Click up, or click down, yeah? Give you one more, one less, yeah? Kind of simple machines, but they were kind of really big, massive things. And they carried out, as I say, fairly simple calculations, nothing very complicated, really, even though it's a very complicated machine. The job it did wasn't very complicated, kind of simple. It's a bit like the abacus in a sense. Yeah. It's very limited and it was expensive. So, the people who had this would be only the richest people, right, would have this, maybe a government or something. Excuse me. And anyway, most people just said last week we're using printed tables like this. These were put together by people, right? People would actually sort of do the calculations. The computers, the people, would do the calculations and then they'd write these down and print them and then people would use them. So that was the way that the ability to calculate was used by ordinary people. Basically like looking at a book. Things like that. When I don't know if you ever do this, but when I was in school, we used to have these funny printed tables for doing mathematical calculations. We've all got smartphones now and calculators, so difficult to imagine people needing these now. Just to remind you about Charles Babbage, right? Remind you of this. I think it's an interesting little story. 1822, he came up with a new mechanical device. We mentioned this last week. It's the difference engine, yes. And you see this huge thing, right? They didn't actually build this. I'm not sure if this is actually the difference engine or the analytical engine. They didn't actually build this at the time, but he designed it. They never actually finished it. Yeah, but you see the size of this thing. They did actually build it in the 1990s, quite recently. It works, right? And then he had a better idea, again, as you mentioned last week, the analytical engine, which was the first computer. It's a bit more complicated. It's able to do different kinds of jobs, more sophisticated jobs. And we kind of think of it as the first computer. It could do lots of different kinds of calculations. It wasn't just multiplication or division, subtraction and addition. It was kind of doing, quite complicated stuff. And it had a memory, right? It could remember things, and a printer, actually, yeah? Although they never actually built that either, yeah? And you remember Ada Lovelace? She's important. She was Babbage's friend. Remember the story? I did this before, that her mother hated her father, basically, right? I thought he was a complete lunatic. And she forced her child to study mathematics very seriously. But she was Babbage's friend. She was the daughter of the poet Lord Byron, right? This is where poetry, literature comes together with computers. And she took the idea and wrote the first computer program. That's the story, right? So she kind of did a translation of Babbage's work and then wrote some notes. In it, she kind of came up with the first computer program. So that's Ada Lovelace, the daughter of Lord Byron. Here's Benjamin Franklin. He's kind of important in this. Founding fathers of America. He did research on electricity. So you get electricity kicking around here. Here's William Faraday. Yeah. And he came up with the electric motor. You probably did some of this in school, I don't know. And with electricity, the use of electricity in machines, calculations could become faster. Right? So think electricity here, right? This guy is Herman Hollerith. He's quite an important character. The American businessman and inventor. And he used mechanical calculations with electricity. So, electricity it helps us to speed things up. I suppose you could say that even today, oops, somebody coming in. Right. Even today, I suppose you could say that we're using, here's my old smartphone. Everybody says that's rubbish. But anyway, I suppose, it's electricity is what allows us to speed up calculation. And we'll see that the way this is done, written in a way, hasn't really changed very much, but it does speed things up. So electricity really helps. The tabulating machine, you can see this is Hollerith's tabulating machine. And you can see that these, oops, what's happening here? He's clocking up, one up, one down, one down, one down, right? Doing these funny little calculations, and you can see the wire, the electric wire, oops, doing that. And he was using these kind of punched cards to put in information and get information. So the printout, I suppose, was quite important. And he founded the Computing Tabulating Recording Company. The Computing Tabulating Recording Company. Sounds good. All right. Well, actually, it doesn't sound good. It sounds stupid. And they renamed it in 1924. So this is Hollerith's, this is Hollerith's company. So it comes up, this is the tabulating machine. Here he is, Hollerith. Okay, there he is. So it comes up with the tabulating machine. They're using that. He founded the Computing Tabulating Recording Company, and then in 1924 they renamed it International Business Machines. International Business Machines, IBM, which you've probably heard of. So that's kind of interesting. And you think it's electricity, on, off, on, off, on, off. Okay. So that's IBM, whatever tabulating machine company. Anyway, so imagine this is all happening, and you go into the 1920s now, and the world population is growing very fast in the 20th century. Yes, so the world population is growing. You can see it's kind of booming around this time, right? So in the 20th century, it starts to boom. And then we think maybe now, later, it's going to go down again. Don't hear about that very much, but it seems like it's a possibility. Anyway, as the population increases, we need to process data. Yeah, data becomes more and more important because our societies are becoming more complex. We need to do calculations more and more. And now we've got electricity, so we have a chance to do this. So by the mid-20th century, we're ready for, and as I said this last week, the first digital computers. Now, I want to do this more than once because I want you to think about this a little bit, right? Digital communication. On, off, 1, 0, true, false. How about human language? Here's the Harvard Mark I. Now you can see this is a computer. And you can see the size of this thing, right? Absolutely enormous, right? And this is IBM in 1944, and absolutely gigantic. And even though these things were so huge, they didn't do that much. I mean, compared to a little smartphone, like my little smartphone, can't see it? Compared to my little smartphone, kind of not very good. So you see the size, massive things. And you're using electricity, it's doing on, off, on, off, on, off. Ones and zeros, ones and zeros. True and false, true and false, true and false. So they're huge, but your smartphone, the smartphone you have now, maybe you're using your smartphone to listen to this class, which is pretty incredible. So maybe your smartphone is what is. I mean, your smartphone is much more powerful than this huge machine. Yeah. And if you're thinking 1944, that's not that long ago, right? I mean, I was born about 10, 12 years later. So that's kind of, a short time in history. We've gone from these massive, not very impressive calculations to tiny smartphones, which can do much, much, much more. Anyway, they're still using punch cards to put in information and get information out. And the basis of this thing was what they called the mechanical relay, right? And that's going to be in the quiz. Mechanical relay, right? And the basic idea is that, you got this source of electricity, right? And it's either in the on state or the off state. On, off, on, off. I mean, this is the simple, theme here, right? The basis of machine communications is ones and zeros, or on, off state, or true and false state, that kind of thing. Yeah. Go into a little bit. So mechanical relay is working a bit like this. You've got these two wires, as it were, right? Two wires like that. And you've got this electrical coil wire here. It's my terrible drawing. Sorry about that. Right? You've got this electrical coil wire there. For electricity to flow, right? And you've got this control wire there, okay? And then you've got this open closed door there, right? So it's like when you have the electrical current, the electric comes through this coil, goes through here, boing, like that. And when that happens, it closes the door. The door closes. And then when there's no electrical current coming through, you switch the electrical current off, then the door opens. So it's just on, open and shut, on and off. That's the basic idea, right? I'm not going to go into any more detail than that. Just ons and off, on and off, open, shut, true, false, ones and zeros. That's it. And it's so, you know, could do this about 50 times per second. So I'm doing this now, right? That's not very often. That's like 1 time a second, right? So even like these huge, not very good machines, they're going 50 times a second, which seems very fast. But if you think about the same kind of calculations with our smartphones, that's going to be, this is 50 times a second is nothing, really. So, but anyway, they're faster than us, right? So human beings, our calculations, the ability to do these things isn't very good, right? Some things we're good at, some things we're not good at. And switching things on and off very, very fast, we're not very good at that. So they're definitely faster than us. But they could only do about these huge things. Could only do about 3 calculations per second, like a addition and subtraction, adding and subtracting. Only about 3 calculations per second, which is pathetic, right? Like this huge, massive thing. Look at it, the size of that, and all the electricity they must be using, and they're still only doing about 3 calculations a second. That's really terrible. And then division and multiplication was really, really slow. I mean, you know, you'd have to wait around for these calculations. So if you think about the size of that, so you think of how computers have changed. Now they're pretty amazing. Also, there are lots of moving parts. Oops, somebody coming in. Right, lots of moving parts. So, for example, if you've got the, let's have a look. So you've got these on, off, and this funny gate, these relay gates, right? That's going to be moving around, right? So some things are moving. And if some things are moving, right, that's going to break down. Right? Something that moves is going to break eventually. And they used to break down all the time. They used to overheat because there's all this moving around, on, off, on, off. Things moving, it get too hot, and then they break down. And sometimes insects actually flew inside and stopped the machines working. So you get like an insect, like a moth or something like that, would fly into the machine, right? And they stop it working. And this is actually the origin of our expression, computer bug. English linguistics. Yeah, we talk about bugs now. It's got a bug. Well, originally they were actual bugs. Right? They flew in. Okay, and then later you got these vacuum tubes being used. Oops. Yeah. So again, you get the electrical current going on, off, on, off, on, off across these electrical vacuum tubes. And in this case, there's no moving part. Yeah. It's the same on-off switch, basically. Yeah. It's either in an on state or an off state. 1 or 0. True or false. But there's no moving parts. So it's a bit of an improvement. Yeah. Nothing's actually moving now. But they overheated. They did get very, very hot. And sometimes they broke down, certainly. But they were better than mechanical relays where there's an actual thing moving, right? Then you get things like the Colossus Mark I coming a little bit later with the vacuum tube. See, the Colossus is huge, right? Absolutely huge. But things are moving, getting faster, and they're doing better calculations. They had 1,600 vacuum tubes. To show you this vacuum, these are the tubes, right? Like that. Yeah, it's 1,600 of those to do the calculations. And it was programmed. They actually did, tell the computer to do things by using electrical wires all over the place. You can see these wires going in all over the place. It's incredible, really. But the the wires are kind of telling the computer what to do at what time. ENIAC, right? Here's one of the vacuum tube computers at the time. You see them putting these wires in to tell the computer to do certain things at certain times, come on at this point, come off at this point, things like that. The electronic numerical integrator and calculator. Wow. Electronic numerical integrator and calculator. Look at the size of this thing. So it was electronic, it was using electricity. They could program it with these wires, and they could tell it what to do, and it was much faster than previously. But these things did still break down, right? They get too hot, they break down. About twice a day, the machine would just stop completely, right? Compare that to today, where we're using our smartphones, and you think, well, how often do these things break down? Probably not very. And I haven't had any problem with this class so far. Fingers crossed. In 1947, so you could see, like, after the Second World War, or going into the period of Second World War, because war, right? You need better calculations. It puts pressure on things to improve the ability to calculate. And then around this time of the Second World War, the transistor was invented. Right? That transistor is rather good, rather important. Bit difficult to understand. I don't really understand it, to be perfectly honest, how it works. But it's still ultimately just an on-off switch. Yeah. Talk about semiconductors, half on, half off, right? So it's really just ultimately it's just an on-off switch. As I say, the science behind transistors is rather difficult. I don't understand it, but it's basically just an on-off switch. So you got things like this. You got two electrodes, these wires, right? Two wires basically, and you've got this thing here, right? That's a semiconductor, right? And then you get a control wire here, and the electrical charge comes in here, and it may be positive or negative. If it's positive or negative, right? Positive, negative, positive, negative, positive, negative. And it's controlled to set it on or off, basically. Yeah. It's either on or off, plus or minus, 1 or 0, true or false. And it can do this many times per second. So that was a big breakthrough, right? But you can see the whole point is really just still ones and zeros, or on and off, or true or false, just two states, a binary state, many times per second. And then transistors and computers got smaller, so it's still massive, right? You see these things are huge compared to today, but they're getting smaller with the transistors. This is the IBM 608 from 1957. So this is after I am born. I'm a baby at this time. They got these computers and they are actually getting smaller. Still huge, but they're getting smaller, getting faster. And then so transistor-based computers start to really improve very quickly and get much smaller over time. And today's computers contain incredibly small transistors. So your smartphone has transistors doing on, off, on, off, on, off, on, off, on, off, incredible numbers of times. And it's got loads of these things inside doing it very, very, very fast. So today's computers are really fast and very small. Here's the Santa Clara Valley. Now, when they were inventing the transistors, they decided a lot of these people moved out to the Santa Clara Valley in California, And silicon is usually used to make semiconductors. Right? Silicon is something like that. It's a funny metal. Right? And when you're making semiconductors, making transistors, tiny transistors, semiconductors, you usually use this material, silicon. It's the best material to use. So the Santa Clara Valley, where many of these transistors were made, became known as Silicon Valley. And we use the word digital so much now, right? We're always saying this is digital, this is digital. It's easy to forget what it means, right? What does it mean? Well, it basically just means ones and zeros, right? It's numbers, basically. Digital just means numbers. And in particular, in this case, we're talking about only two numbers, binary state, ones and zeros. So numbers. Yeah, as you can see with machine 1 0 0 1 1 0 0 1 0 1. That's it. For computers, just ones and zeros. Yeah. But I won't go into why it's only ones and zeros. It's kind of easy. It's either on or off. It's simple. Yeah. It's kind of clear. Yeah. So it makes it easier for machines. So they're huge. You go for huge, slow computers with mechanical relays and moving parts with insects flying inside, breaking them down all the time, and your smartphone, right? So here you've got like tiny transistors, semiconductors, tiny semiconductors, incredibly small, doing incredibly fast calculations. But they have the same basic system, right? So when you're looking at these early calculations with moving parts and insects all over the place, and your smartphone, it's the same basic idea. Ones and zeros, ones and zeros, ones and zeros, ons and off, on and off. And so it's the same basic idea for communicating with machines. And, I don't know if you would agree with this, but I would say, ultimately, even how great these things are, amazing things, particularly for an old person like me, to think, wow, look at that. They're still kind of stupid, right? That's all they understand is ones and zeros. Don't understand anything else. Just ones and zeros, that's it. On, off, 1 and 0, true and false. That's it. Let's have a look at this guy, William Shockley. He's kind of an interesting character. Okay. He got the Nobel Prize for Physics in 1956, the year I was born. And he did lots of research on semiconductors. So we get advances in semiconductors. He moved to Silicon Valley, actually, in 1956, I believe. And he founded the company called Shockley Semiconductors. That was the original name of the company. It later became the Fairchild Semiconductors company. And eventually, later, they changed the name to Intel. Yeah, so Intel. You'll see Intel all over the place. I think the Apple smartphone has Intel chips inside. So the company became Intel. That was founded by this Nobel Prize winner, research on semiconductors. And now it's the largest computer chip maker in the world. Apple beginning to challenge that. So on-off, that's what it is. Right? It's just ons and off, on and off, on and off. The whole thing is based on that. Remember Richard Montague? Now we're going to get into semantics a little bit. Just review that we talk about ones and zeros, ons and offs, right? Remember Richard Montague? He's a very famous person in semantics. I'll just remind you, he was an American mathematician, philosopher. And he lived 1930 to 1971. He died when he was 41. Very mysterious. Yeah, he died when he was 41 years old. Violently murdered in his home in Los Angeles in 1971. And he's famous in semantics because he believed that natural human languages and artificial machine languages are basically the same. Is it true? Machine languages, 1 zeros, 1 0, 1 0, 1 0, 1 0. Human languages, natural languages, are the same. Think about it. I don't know, right? Just get you to think about it a little bit. But I'll say that again. He believed that human languages and artificial man-made languages are basically the same. What do you think? I don't know, right? Artificial man-made languages, what's that? For example, formal logic, right? Computer programs would be another example, right? But formal logic, as we mentioned, you can translate from English into formal logic, and that gives you the real meaning. Is this what he's saying, right? What is true? The meaning of the sentence is what makes that sentence true. True, false, 1 0, on, off. So translate into formal logic, what does that mean? For example, Jill sees John. Just review this. Translate into formal logic, and it'd be something like that. Jill sees John as a human language sentence. Translate into a machine language that a computer can understand. And you can do it. Just have a quick review of propositional logic. If P, then Q. This is a sentence. This is a sentence. If P, then Q. There's no internal structure. Sentences are represented as letters. P and Q. P is a sentence. Q is a sentence. Any proposition can be either true or false, on or off, 1 or 0. See the point? So that's really how machine language and semantics, English semantics, comes together. 1s and 0s. So that sounds familiar? You've got the old, mechanical relay. Can't do it like that. The mechanical relay, on and off. The electrical current makes it on or off. Here's George Boole. George Boole, Boolean. He's a British mathematician in 1815 he lived from 1815 to 1864. And he invented Boolean algebra, which was binary. We got two states, on and off, 1 and 0, true and false. Yeah, so the whole basis of that. And so, when computers were taking off, right, when computer programming was starting seriously, when we're inventing computers, trying to communicate with machines, Boolean algebra already existed. Right? So people started using Boolean algebra. It's on and off, on and off, on and off. That's it. And we can use binary alphabet for communicating. For example, A could be written like this. B could be written like that with just 1s and 0s. So that's a possibility for communicating code, for example. So we could communicate by doing that if we wanted, just ons and offs. But it'd be very slow for us. We're not very good at this, right? If we do it, we're really, really slow. But computers, machines can do it really, really fast. No problem for modern computers. Okay, then. Let's take any sentence. John is hungry. P equals John is hungry. P equals 1. P is true. John is hungry is true. Let's take any sentence. John is hungry is true. John is hungry is false, right? P equals 0. John is hungry is false. So it's either on or off. It's the same thing. So not P, right? Not P, let's review this again. Not P the minus, not P is 1. That means not P is true. So Boolean algebra, everything is either true or false. And also there's 3 basic operations. There's the not operation, there's the and operation, and there's the or operation. Not, and or. Everything is either true or false, and 3 basic operations. And that's pretty much it, actually, right? We're not going to do much more than that. P, not P. P and Q. P or Q. So, why should you care? I suppose, well, basically, the thing is that linguistics, semantics, right, formal semantics, and computers, they're making use of Boolean algebra in a big way. Right? They're using this system of ones and zeros, ons and off, true and false, as a way of translating, I suppose, natural language into an artificial language. There's Boolean algebra. The not operation takes 1 input and gives 1 output. Input P, output not P. Input not P, output is not P, which is P, right? So the input is not P, the output is not P, which is P. So it just reverses. It reverses the truth value. And the AND operation takes 2 inputs and gives 1 output. Input P and Q, output P and Q. Right? If P and Q is true, then P is true and Q is true. The OR operator takes 2 inputs and gives 1 output. Input P and Q, output is P or Q, like that. If P or Q is true, then either P is true or Q is true. Yeah, it's easy, right? And you've got these truth tables, right? So the yes input does nothing. You put in an input of 0, the output is 0. The input is 1, the output is 1. It does nothing, basically. It's just yes, that's true. The not input, the not operation, rather, gives you the opposite. So if the input is 0, you reverse it to 1. If the input is 1, you reverse it to 0. The AND operator takes 2 inputs, A and B. If A is 0 and B is 0 and the output is 0, it's not AND, right? If A is 1 and B is 0, then the output is 0. If the input is 0 and the output is 1, the output is 0. For AND to be true, A and B is true, then A has to be true and B has to be true. And the OR works in the same way. Yeah, so those are called truth tables. That's how we represent natural language as a machine language formula. So propositional logic, if P then Q, this means if P then Q. If not P then Q. If P then Q, this means if P then Q. If P then not Q. Okay, so you get the idea. I'm not going to go into too much to this. For example, John is hungry is P, John eats is Q. So you say if P then Q, what does that mean? Well, that means if John is hungry, John eats. Yeah, that's simple, right? And then another example, John is hungry is P. Q is John works. So, for example, you could say if P, then not Q. What does that mean? Well, that would just mean if John is hungry, John doesn't work. Yeah, that's common sense. It doesn't have to be common sense, right? It could be anything, but that gives you an idea. That's all it is. It's really simple, right? And it's ultimately just about ones and zeros, ons and offs, true and false. If P then Q, there's no internal structure, as we say. But of course, language isn't like that, right? I mean, we don't use this P's and Q's in language, right? So then we have predicate logic. All right, predicate logic means like a verb, right? You see why I've made you think about this before, because I mean, it's quite a lot of stuff. It's not very difficult, but you have to think about it a bit. Let's say, for example, you've got a predicate like loves, right? Now the computer doesn't know what that means. The machine doesn't know what the loves means, but just we try and remember what it is. Helps us maybe to use these here. So loves J, M might be something like John loves Mary, for example. Now this does have internal structure. Here's the predicate and here's the arguments. Right? It does have internal structure. This might mean, for example, that John loves Mary. It doesn't have to mean that. It could mean anything, really. Right? Up to you. Yeah, whatever you do, say you're programming the computer, it can mean anything you want it to mean. And then if you say something like this, think about what does that mean? You can probably work that out. But this probably means that, for example, John does not love Mary. Yeah, it doesn't have to. Could mean anything. But it means not something, right? It makes sense that we would use loves to mean loves. You've got something like this. Let's try and work out what that might mean. So that might mean, for example, John loves Mary but does not love Bill, right? So John loves Mary, but and he doesn't love Bill, maybe. John doesn't. J and B doesn't have to be John and Bill. J and M doesn't have to be John and Mary, but it's common sense to do something like that. Imagine it's the basic idea is imagine you're putting information in a computer database. You're telling the computer something about the world. You're creating a world. Yeah? You are creating a world. Maybe it's real, maybe it's not. Let's give you an idea here. But the computer doesn't know, right? The computer doesn't know if it's true, false, really. You're just telling the computer. So Japan is a country, works like this, country, like that. Yeah. You've already been through this. Japan is a country. Don't forget the computer only understands ones and zeros. Yeah. Doesn't know what a country is or what Japan is. Unless you tell it. Easy, so it's kind of easy, isn't it? Right? Yes. But what's the point, I suppose, right? Well, it just helps with computer programming, right? It's kind of the basis for computer programming, really. Predicate, logic, and so on. And we use it to input data. You input data, you create a world. You tell the computer what is true in this world. And you write code. And of course, the computer is very fast. It helps us, right, to calculate in ways that we just couldn't do. So they're very clever in some ways, but they're also kind of stupid. Yeah. Because they only understand ones and zeros. In fact, they don't really understand anything, right? Apart from ones and zeros. They're a tool. Yeah. Computers are a tool. And I think, that's where maybe you think, well, is human language and machine language the same? Now, I don't know, but other people are not tools usually, right? They're not our tools. We're cooperating together to do something, whereas computers are a tool. They're not really cooperating. We're not really cooperating with computers. We're using computers. That seems to be a big difference. But anyway, we have to put in the data, and we can put in any information we want, and it can be useful. That's a mistake. Should be useful. Or it can be complete nonsense. It doesn't matter what you put in, really. You can put anything you want. So predicate logic. I think I'll stop here, actually, pretty much. Let's put in the computer, we decide a predicate, and the predicate has arguments. So for example, Peter fell over. You did this last week. Predicate like a verb, fell over. It's probably going to have one argument. Jim donated $100 to the city hospital. Was the predicate? Donated. How many arguments? Probably 3. Yeah. What are the arguments? Something like that. So it's going to be like this. Jim donated $100 to this city hospital. Now, it doesn't have to be like this. And you can basically use anything you want to put in the information. But it makes sense that you would use words that make sense to you. It's another way of putting it in. Yeah. Ben hates computers. How would you do that? Simple, right? Eddie gave up. What would be that? What's that? Something like that, maybe. A predicate with one argument. Emmy's a genius. Probably something like that. So there's basically no limits. I mean, you can do whatever you want as long as you know what the information is that you're putting in, and you can make sense of it. That's okay. The computer doesn't know, right? Computer doesn't know who Emmy is, right? Computer doesn't know what gave up means, right? You're just putting the information in so you can use it. And you can basically, if you want to have more than 3 arguments, you can. For example, you could say Mary visited Family Mart on Saturday, 15th of April, right? So this is not an object. This is an adverb, right? But if you want to do that, you can, right? So you're just organizing your information. So in computational linguistics, you have a verb, subject, and a complement. So hit would be, think of hit, how many arguments would hit have? Probably going to be 2. Would be like that. Remember propositional logic? If X, then Y. If you study hard, you will pass the test. X is you study hard. Y, you will pass the test. So you can use it to tell the computer about the world. If X, then Y. If you study hard, you will pass the test. Or you could do it like this, with predicate logic. If Emmy studies hard, then Emmy will pass the test. That's easy, right? If Emmy studies hard, she will pass the test, would be the natural language formula. So basically, you're just imagining very simple worlds, and you're telling the machine about the simple world. In this case, it's a very simple world. I'm going to stop there, actually. I've got a few examples to do. I'll do that next time, I think. Just do a quick review, because I'd like you to keep thinking about this natural language and machine language, and think about the differences and similarities between those things. But I think I will give you a chance to, let me just come out for a second. When did humans discover time? When did they know time existed? Oh, wow. That's a good question, actually, isn't it? That is weird. Yeah, you wonder if maybe if we discovered the technology for measuring time, and then we realized time existed. Maybe we needed to discover a technology for measuring it, right? Maybe by accident, before we had any awareness of time itself. But that's a good question. When did humans discover time? When did they know time existed? I don't know, right? I don't know, but I suspect it's connected with our ability to measure it. But who knows? Don't know. Good question, though. Very good question. I don't know the answer. Yes, put that in your dissertation. Right then. Anyway, I'm going to just very briefly go into the thing again. And where is it? I've lost it. Okay, web class here. So here's the quiz. Quiz is going to be open now. And I'll just, okay, there we are. There's today's quiz. And the magic word today is semiconductor. Let me just put it in. SEMICONDUCTOR. Semiconductor. That's it. Okay. Right then. So in that case, I think, no problem. Yeah, I think we're all right. I'm going to do a quick review of this stuff next after the vacation, but it's going to be pretty simple stuff, so don't worry about it too much. And then we'll go into pragmatics, thinking about how humans actually communicate. And I want you to keep thinking, right? Just keep thinking about the differences and similarities between human language, natural human languages, and artificial machine languages. That's really the point. Okay, then, guys. So if there's no questions or comments, I'll give you a bit of time to do the quiz, and I'll see you after the new year, which I believe will be the 8th. Okay, then, guys. So if there's no questions, I'll say bye-bye. Bye-bye. Thanks very much, then, guys. So if there's no questions, any questions? Probably just having a cup of coffee or something. Okay, then, guys. So I'll close this down. Have a nice Christmas and Happy New Year. I'll see you in January. Bye-bye.